Welcome to our next video in which we're going to learn about the rainbow demo leading us into something called the water dissociation constant and pH, and something related to pH that you may not have heard about is called pOH, and so you'll see how those work when we get to them. So in part one, we're going to look at the relationship between the concentration of hydronium ion and hydroxide ion in water. And I want you to watch the rainbow demonstration video on YouTube. I've got it linked in the assignment as well. This is something that I would do in class, but obviously won't be able to do so. So go watch the video and then we'll come back and discuss it. I hope you watch the video now. So in the video, she starts off with some hydrochloric acid, a 0.1 molar solution of hydrochloric acid, and it contains universal indicator. Universal indicator is this really cool indicator. It's actually a mixture of 4 different indicators that has this great ability. It goes from red, orange, yellow, green, blue, indigo, violet. Yes, the colors of the rainbow, as it goes from acid to base and everything in between. And so when we have a red solution, that means that the solution is acidic. And that makes sense to us, hopefully, because we have that HCl in there. And as we learned, HCl gives us H3O+, which is the indicator of an acid. So here's the reaction of HCl giving us H3O+. Remember that H comes across the acid, gives to the base. We make H3O+, which is aqueous, and we make the chloride ion, which is also aqueous. And it's the H3O+ that's going to be important to us here. Now, if I had done this in class, I would have started with a solution of the sodium carbonate, which she started with, but I would have had the universal indicator in it, and I would have had a violet color. And violet color, as you see on the rainbow up above, indicates that it's a base. And the base now has a concentration of hydroxide in it. Now, where does that hydroxide come from? Because you don't see any hydroxide in sodium carbonate. Well, sodium carbonate is a salt. And this salt breaks apart into its ions. It dissociates. We talked about this back in chapter 8 and in reactions as well. And when we put that in water, water is not really a reactant here, which is why it's up above the arrow. We're going to make 2 sodium ions. Remember that subscript 2 doesn't mean we have Na2. We have 2 sodium ions, and we have a carbonate ion, and those are all aqueous. Carbonate is CO3 2-, and that's aqueous. Now, it turns out that carbonate is a base. And so carbonate as a base, CO3 2-, it turns out that it's the conjugate base of something that takes the H from water and puts it on here. So if this is our base, then what we're going to make, let me use purple now since that's a base, we're going to make HCO3, which is, of course, its conjugate acid, and we're going to make hydroxide, which is the conjugate base of water. So water is acting as the acid in this reaction. All right, so we've got the presence of hydroxide there. Now, when we add the sodium carbonate to the hydrochloric acid, we have another acid-base reaction. This turns out to be a neutralization reaction. We take the HCl and we take the HCO3-. HCO3- is also a base. Yes, it's a conjugate acid. There, it's a base here, which means it's amphoteric. And the reason this is acting as the base is because the HCl is a strong acid. So we're going to take our H plus. Now, this is a neutralization reaction, but it can also look like a Bronsted acid-base reaction. And we're going to make, sorry, you know what I wanted to have? Not the HCl. Sorry about that. I wanted to have my H3O plus. I wanted to have my products up here, my H3O plus and my HCO3 minus. Okay, so forget about the HCl, but H3O plus is still a strong acid. We're still going to take that H and bring it over here. And in the process, what are we going to make? We're going to make water. So there's the neutralization reaction. Now, where does the water come from? It comes from the H3O plus. And we're going to make H2CO3, which is carbonic acid. Now, carbonic acid itself further dissociates, and it makes another water and carbon dioxide gas. And those are the bubbles that you see in the picture down below. So if you look at this picture, you'll see these bubbles forming. The bubbles are forming where we have the neutralization going on, and we'll talk about that now. So this is a way of showing the range of acid to base, demonstrating a series of acid-base reactions in a single test tube. So what's going on? Up near the top, because the sodium carbonate went down to the bottom, that sodium carbonate solution was more dense. So it sunk down to the bottom. Near the top, there's virtually no neutralization. There's no reaction because there was no interaction of the sodium carbonate with the hydrochloric acid. So up near the top, we still have a high concentration. Oops, I thought I picked red. I want red for that. A high concentration of H3O plus. So excess H3O plus means that we have a high concentration of HCl plus. The solution is acidic, which, as we'll learn in a few minutes, means we have a pH below 7. And it also means that if we have a high concentration of H3O plus, the concentration of hydroxide is low. And we'll talk about that. We'll see how that works in a moment. In the middle, there's been enough of the hydrogen of the sodium carbonate making its way up to the middle that we have neutralized. So in the middle, we've managed to neutralize, and now we have the same number of moles of the acid and that original base, the CO3 2 minus. So we have a neutral pH, a pH of 7, and in this case, right where it's green, we have the concentrations of the hydronium ion and the hydroxide ion being equal. And that's going to be our definition for what a neutral solution is. Finally, near the bottom, we have over-neutralized. We have excess base, because we neutralized the HCl, and then we kept adding more base. So we have excess carbonate. Excess carbonate means now that the hydroxide concentration is high, right? So up above, we saw that concentration of hydroxide coming from the carbonate. That's high. We have a basic pH that's greater than 7. And because the concentration of the hydroxide is high, the concentration of the hydronium ion has to be low. And so that's a seesaw effect. If the hydroxide is high, hydronium is low. If hydronium is high, hydroxide is low. This seesaw effect we've found before to be an inverse relationship. So there's this inverse relationship between the concentrations of the hydroxide and the hydronium ion. Why should this be? This comes about because water itself, even in neutral water, is not just sitting there. Water has what we call a self-ionization. A self-ionization. So acids ionize to form hydronium ion. base is ionized to form hydroxide ion. Water itself undergoes this ionization in which two water molecules interact. One of them acts as an acid and gives up a proton. So let's take that proton. One of them acts as a base and accepts that proton. And what we end up with is the following. We end up with hydroxide, which is the conjugate base, and we end up with hydronium ion. Now, we usually write the hydronium ion first, traditionally. I'm not sure why we needed to. And that's our conjugate acid, this hydronium ion. This reaction is going on all the time in neutral water. And this double arrow indicates that this reaction is continually occurring, that we're continually making those products, and then those two products will come back together to form water, and they continually go all the time. Now, this reaction actually goes very little. I'd actually want to draw this reverse arrow a lot bigger, because this reaction has very, very, very little in the way of products being formed. And we know that because this dissociation constant, K stands for constant, W for water, the water dissociation constant, which equals the product. So this is the product of the hydroxide concentration of the hydronium concentration, is a very, very, very small number, 1.0 times 10 to the minus 14. We'll talk about what that means in a moment. Okay, and this is at 25 degrees C. That value does change depending on temperature. So because of that reverse arrow up there, if we add some excess H3O plus, so as acid is added, the H3O plus concentration increases. That means that this number is going to be too high. And what that's going to do is cause us to react, and as it reacts, it's going to decrease the concentration of the hydroxide ion until we bring that concentration, those concentrations, the product, back down to 10 to the minus 14. If we add base, we have excess hydroxide. Let me use a different color since I've used purple up there already. So we have an increase in the concentration of the hydroxide. So now the hydroxide concentration is too high. Again, because that's too high, we have to come back to this number. We have to bring these concentrations down. So the reverse reaction is going to react, and we're going to bring down the concentration of the hydronium. And so it turns out that this is what drives all acid-base chemistry. In neutral solution, the two concentrations are going to be equal to each other. So the two concentrations, so we see, if we call each of those concentrations X, those two concentrations are each X. But what is this number? This number is X squared, right? It's X times X is X squared. So X is going to be the square root of 1.0 times 10 to the minus 14. And that is equal to 1.0 times 10 to the minus 7. Now we have to put back the molar. That unit, that kW doesn't have units, but for concentration, we need to have molar. And so this is the concentration of the hydronium ion and the hydroxide ion in neutral water. Very, very, very little bit. It's there whether you want it there or not, but it's not enough to cause any problems. Such low concentration. And you'll notice there's that number 7 in there. And we'll come back to that number 7. We'll come back to that number 7 shortly. All right, so let's see how this affects water chemistry. If we have excess hydronium ion, so let's say I give you the concentrations of either the hydronium ion and the hydroxide ion, you can use that Kw equation to calculate the value that you don't have. So if I give you the concentration of the hydronium ion, say it's 8.9 times 10 to the minus 9 molar, just picked a number. The hydroxide concentration, let's write the equation down below. We know that the Kw is equal to the hydronium ion concentration times the hydroxide concentration, and that equals 1.0 times 10 to the minus 14. So if we rearrange that, if we know the hydronium concentration, then if we rearrange that to find the hydroxide concentration, that's going to be 1.0 times 10 to the minus 14 divided by the hydronium concentration, or in this case, 1.0 times 10 to the minus 14 divided by 8.9 times 10 to the minus 9. You can drop the molar in there because there's no molar in our unit, but make sure you put it back when we have the hydroxide concentration at the end. And when you do that math, we get 1.1 times 10 to the negative 10 to the negative 6 molar. And if we take that and multiply it back to H3O plus, we should get 1.0 times 10 to the minus 19, 10 minus 14. So notice, compared to 10 to the minus 7, the hydronium concentration was low, and so the hydroxide concentration came up a little bit. We can do the same thing to solve for the hydroxide concentration. Now, in the homework, I'm going to give you something like this, where I give you the concentration of a strong acid or a strong base. In this case, the strong base, in a strong base, the hydroxide concentration is equal to the concentration of the base. For a strong acid, it would be the same thing. So if I give you a strong acid, say HCl, the concentration of the H3O plus is going to equal the concentration of the acid that I give you. And that's because these guys ionize 100%. That's the definition of a strong acid and a strong base. So the hydroxide concentration in this solution is going to be 0.025 molar. So the hydronium concentration is going to be H3O plus. I'm going to shorten this a little bit. Is going to be the 1.0 times 10 to the minus 14 divided by the hydroxide concentration. I've just rearranged the equation up above like we did in letter A. 1.0 times 10 to the minus 14 divided by 0.025. Notice 0.025 is a lot bigger than 10 to the minus 7. So this number for the hydronium concentration is going to be a lot smaller. And in fact, it's 4.0 times 10 to the minus 13 molar of the hydronium ion concentration. So that's an easy kind of calculation to do. Now, what does all this have to do with pH? So those numbers with the 10 to the minus 14, 10 to the minus 9, 10 to the minus 2, those numbers are all over the place. And it's difficult to compare sometimes numbers that have that big a variety in their exponents, because 10 to the minus 13 is basically a billion times smaller than 10 to the minus 5. And how do you or 10 to the minus 4? So how do you compare those values in a nice, easy to look at way? So scientists came up with this concept of pH, and yes, pOH. pH stands for the power of the hydronium ion concentration, or the power of hydrogen concentration. Now, on your reference chart, this is one of the first equations you're going to see under acids and bases. We shorten it to H plus just to make it easy, but I want you to keep in mind H plus is always shorthand for H3O plus. So what this log function, it's a log, so pH is the negative log of the hydrogen concentration. And this negative log makes it easy to compare large differences in concentrations. And it's negative because most calculations, most of these concentrations are less than 1. And so what it does, it turns it into a positive number. Now, you can have negative pHs, and I'll show you how that works in a few minutes. And so if you have a hydrogen concentration, you want to calculate the pH, you just take the negative log of it. Now, it becomes relatively easy to do if you have a concentration where you have a 1.0 times 10 to something. If you have that 1.0, then it makes it pretty easy. I'll show you how that works in a moment, but put this into your calculator now. Take the negative log of 1.0 times 10 to the minus 6. So negative log of 1.0, you can put another 0 in there, doesn't matter, times 10 to the minus 6. What you should get is a negative 6. And I'm going to put a 0.00 there because I want you to always use 2 decimal places for pH, even if they're zeros. Okay, so make sure you put those zeros in there. In general, if we have that 1.0 as our coefficient in the scientific notation, 10 to the negative x, so any x, the pH is going to equal x and 0.00. So 10 to the minus 6 is a pH of 6. 10 to the minus 5 is a pH of 5. 10 to the minus 10 is a pH of 10. So it makes it pretty easy to do those calculations. However, you're not always going to have 1.0s if you have something other than the coefficient of 1. So if your H plus coefficient is anything other than 1, you've got to use your calculator. And so for this second example, we're going to take the negative log in your calculator of 2.3 times 10 to the negative 12. By the way, this is log base 10. Make sure you're not using natural log. You're going to get some weird results if you use natural log. And that's going to equal 11.64. And there's our two decimal places. If you want to go the opposite way, what's the inverse function of log? Well, the inverse function of log, some calculators have an anti-log button, and that would be the inverse function. But most calculators these days speak more English than math. And so there's a 10 to the power button. And that 10 to the power button should be the second function on your log key. And so the opposite of pH is 10 to the negative pH. And this is another equation that's on your reference chart, 10 to the negative pH. As before, if we have an x 0.00, we're going to take that x and we're going to say that the hydrogen concentration is just 1.0 times 10 to the negative x. I want you to always write the hydrogen concentrations like this. Or you can write them in decimal form if it's like 0.1 or 0.01. Don't leave them in just 10 to the minus x. So if we have a pH of 5.00, 10 to the minus 5.00, let's take that 5 there, and we just turn that into 1.0 times 10 to the minus 5. Oh, and we need to have the molar after there because it is a concentration. If the pH doesn't have a 0.00 there, then again, we can't leave this as 10 to the negative 8.95. That really doesn't mean anything to us. You've got to do the math on this one. That is the math. So set that up in your calculator, 10 to the negative. Don't forget to put that negative in there, 8.95. And we're going to get 1.1 times 10 to the negative 9 molar. So that's how we do these pH calculations. I said this up above. If we have a concentration, if we have a strong acid, 100% ionized, so the concentration of the acid is equal to the concentration of the H3O plus. So I tell you, we've got 3.8 times 10 to the minus 2 molar solution of HCl. So the concentration of the H plus is 3.8 times 10 to the negative 2 molar. And the pH is just going to be, take the negative log of that, negative log of 3.8 times 10 to the minus 2 molar. And that's going to equal don't need the molar in there, 1.42. Now, to the right here, we have a chart. showing us the relationship between the hydroxide concentration, the hydronium or hydrogen concentration, and pH. And so up above here, you see the H plus concentration going from high to low. So as we go from high to low, we're getting to, going to the right, we're getting to neutral, and then we're getting to basic solutions. And the pH up above, notice the pH just takes that negative log there. So these are simple pHs, negative log of those numbers. You can have a pH that's less than 1. How can you have a pH that's less than 1? Suppose you have a hydronium concentration of 10. 10 is 10 to the first, right? So if it's 10 to the first, what's the negative log of 10 to the first? Do it in your calculator. You'll find the negative log of 10 to the first is a negative 1. So negative pHs do exist, and these are very strong. pHs of greater than 14 can also exist. So if we have a 10 to the minus 15 molar, you can have 10 to the minus 15 molar. It's just very, 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 very weak acid. That would have a pH of 15, and then that's going to be very basic, very strong on the base side. Down below, we have the concentration, and right in the middle, of course, is neutral. And neutral, pH of 7, 10 to the minus 7, hydroxide concentration, 10 to the minus 7, hydronium or hydrogen concentration. And you see that as the concentration of the acid goes up, so this is strong acid, so if the concentration is high, by the way, if the concentration is high, the pH is low. That's how pH works. Concentration of the hydrogen is high, pH is low. Down here, the hydroxide concentration goes the other way. And now we also have something called the pOH. So pOH, we're not going to go through calculations because in the notes because they're exactly the same as the calculations for pH, but exactly the same kind of situation. pOH is the power of hydroxide. And so we can do the same kind of thinking about hydroxide as with hydroxide of the hydronium concentration, that we can do the same functions and we get the exact same results. Notice that strong bases has a low pOH. The lower the number, the stronger the concentration of that particular item is. So there will be some calculations for that on the homework. And one last thing I'm going to bring in is an easy way of converting between pH and pOH, because that's going to be the easiest way to convert between various acid and base concentrations. So pH and pOH, going back to Kw, remember from the front page that Kw is the concentration of the hydroxide concentration of the hydronium. I'm going to use the hydrogen there. And that's 1.0 times 10 to the minus 14. If you take the negative log of both sides, so negative log of this whole thing, then what we get is the negative log of the H3O plus, so I've thrown the H3O plus back in there, and the negative log of the hydroxide concentration, and the negative log of 10 to the minus 14. Well, that turns out to be the pH. And so that's our pH right there. That's our pOH. Oh, I want to circle 14. pOH here. And 14 is the negative log of 10 to the minus 14. And so this equation that the pH plus the pOH equals 14 is an easy way to convert back and forth between the two of them. Now, let's put that in use for one quick calculation. I'm going to show you how to do this two ways. In the homework, there is a box that's going to show you an easy route to calculate back and forth between the various values that you see down below. So the values, the summary down here between pH, H3O plus concentration, OH, and OH minus. So there's going to be easy ways to convert between all four of those. If you know one, you can get the others. So if I give you this concentration of sodium hydroxide times 10 to the minus 4, 6.02 times 10 to the minus 4, we know that for strong bases, this is a strong base because it's sodium hydroxide. So the concentration of the hydroxide equals the concentration of the base. And so that equals the 6.2 times 10 to the minus 4 molar. There's going to be two ways to go about, and if you look at the homework again, you can follow this around that circle or that box. In the first way, I'm going to take the H plus concentration, the hydroxide concentration. I'm going to calculate the H plus concentration by taking the 1.0 times 10 to the minus 14 and dividing it by my 6.2 times 10 to the minus 4. So taking the hydroxide concentration and dividing that into the Kw expression, and I'll get 1.6 times 10 to the minus 11 molar. So that would be my concentration of the hydrogen or hydronium ion. The pH, then if I take the pH, so I want to know the pH. I'll show you how to do the pOH too in a moment. So the pH, I take the negative log of that 1.6 times 10 to the minus 11, and that gives me 10.79. If I wanted the pOH for this, then I would take 14, and that's 14.00 minus 10.79, and that's going to equal 3.21 would be my pOH. So you can get all the other three that you're missing from the one that I give you. The second way of doing it, rather than going to the hydrogen ion concentration first, let's calculate the pOH first. Now this should be consistent, and if you do this calculation, negative log of 6.2 times 10 to the minus 4, you will get 3.21. So it's a different way of getting the same number. Now pH is equal to 14 minus the pOH, so take that 3.21, subtract it from 14, and you'll get 10.79, and there's our pH. And if I wanted my hydrogen ion concentration from this, I would just take 10 to the negative 10.79, and I should get that 1.6 times 10 to the minus 11 molar. So you can do this either way. Notice you get all the same numbers, 10.79, 10.79. You get those all the same numbers no matter which way you go around that box. One last caution, and then I'll let you go. Watch out for subscripts. Calcium hydroxide is a strong base. So when it dissociates, it doesn't form one, but it forms two hydroxides. So we have to take the hydroxide concentration, we've got to multiply it by 2 in order to multiply the calcium hydroxide concentration by 2. Make sure you do that before doing any further calculations. So this is pH and pOH. I hope it gives you a better understanding, and I will see you in class.